Hey guys, so far what we have been considering is, we have been considering only one kind of an example. Essentially we want to rather permanently deform a crystalline material, and this crystalline material is kept in a force field, let's say magnetic field. Now the magnetic field in which the material is kept, the crystalline material is kept, varies with time, and to that material or to that crystalline metal you are introducing an external load. Now the force experienced because of this load by individual atoms depends on the position of the atoms. So basically, when in response to this introduced load, when the position of the atom changes, this change in the position depends on the load that you impose and also the force field in which the atom is already present and which is changing with time. Now we can move away from this consideration. It will not be a stretch when we say that the force field that we are exposing our material to not only varies with time, but it varies with the position and in a particular way. Let me repeat. When we say that I'm keeping my material in a force field, I'm placing my material in a force field, we initially assume that this force field varies with time. Now what we are doing is we are extending that assumption and saying that this force field is not varying with time now, it is varying in a specific form with respect to my position. So this is not far-fetched, this is something that we can relate to. For instance, I can imagine my material, a block of iron let's say, being placed in a magnetic field. Again, this is purely an example, and this magnetic field is rather inhomogeneous. The magnetic field, let's say, is distributed like this. The intensity of the magnetic field is rather distributed like this. So it means that the magnetic field experienced by the individual atoms depends in a specific way to the position of the atoms. In a specific way, I mean it can be represented as a function of the position. It's not just depends on the specific position of the atom, it depends in a specific way. The magnetic field experienced by the atom, it depends in a specific way to the position of the atoms. So it means the force experienced by the atom is the function of its, the magnetic field experienced by the atom is a function of f of x. Now to such a system, you are imposing a load. To such a system, you are imposing a load, and the force that results from this load, and the atom experiences this force, and this force the atom experiences depends on the position of the atom. So this is something we have considered so far. So we have an external force, and the amount of force experienced by the atoms depends on its position, and this atom is now placed in a magnetic field wherein the atom experiences a magnetic field, and the intensity of it, how much it experiences, depends on a specific relation in the position that is given by this function here. When you take this entire consideration and formulate it in the form of an ODE, you end up an ODE with an ODE like this. So basically, this term here indicates that the force experienced by the atom depends on its position, and this term here indicates that in addition to that force, the atom is placed in a field, and the intensity of this field the atom experiences depends in a specific way on its position, and this specific way is expressed as the function of x. Now basically, what we have is an ODE wherein our base variable, in addition to its derivative form and its original form, now is expressed as a function. A base variable x in addition to its derivative form and its original form. The derivative form and its original form is now expressed as a function. So essentially what we have now is a non-linear ODE. Now this is basically what we will attempt to solve in this lecture. Now in all these discussions so far, we have been considering only one type of physical condition, one type of physical activity, that is deforming our crystalline material. We want to permanently destroy or deform our crystalline material. But fortunately for us, that is not the only aspect wherein the material research is involved. So there are several domains. Now for this discussion, we will consider an entirely different domain. Instead of breaking things and permanently deforming things, for this discussion, we will try a setup wherein we make things, not break things in this discussion. For that discussion, we will consider a setup wherein we will make things. Now one way of making things or producing things is something called as casting. So what essentially we do is, we take our metal, melt it, and pour this molten metal into a cast. Now this is essentially what is being depicted here. Assume that you are this guy with this wonderful suit here, and you are playing with the molten metal, how cool it is. So you are taking this molten metal and pouring it into the cast. Now, these atoms that constitute this molten metal, they experience a momentum when you are pouring it into the cast. And this momentum the atoms of this molten metal experiences depends in a specific way on the position of the atom, and that is governed by f of x. Let me repeat. When you are taking this molten metal and pouring it into a cast, the atoms that constitute the molten metal experience a momentum. The magnitude of this momentum depends in a specific way on the position of your atoms. And such a condition is now expressed as an ODE in this form here. Now the momentum is most and velocity. We have assumed that for the simplicity of our discussion, we have assumed that the mass is unit. So ultimately our velocity is expressed as the first derivative of the position, and this momentum is rather depends on a specific trend in the position of the atom, and that is expressed as f of x. So the momentum experienced by the atom, it depends specifically in a specific manner on its position, and that is described in this way. The entire physical setup is now described in this form here. Now, had this expression been, or had this condition been something like the momentum experienced by the atom depends just on its position alone, we would have an expression like this, and this expression becomes a linear expression or linear ODE, which we can comfortably solve for now. At least I assume that. But now in our case, the key difference is it is not just depends on the position of the atom, but it depends on the position of the atoms in a specific way. There is a specificity to which there is a specific trend in which the momentum is experienced by the atoms. So what we have is a nonlinear ODE with a physical significance which we would like to solve. Now in order to solve that, we assume a point x bar. We assume a position x bar, and at this position the atoms experience no momentum at all. You take your molten metal, you are pouring it into a cast, and as you are pouring it, the momentum experienced by the atom depends in a specific way on its position. Now in order to solve the ODE that results from that case, we are assuming a position wherein the momentum experienced by the atom is 0. That now can be expressed as something like this. We have assumed a position x bar wherein the momentum experienced by the atom is 0. It means I can write this as something like f of x bar as 0, because this is going to be 0. Now under such a case, what I end up having is, when I have f of x bar to be 0, meaning momentum experience at x bar to be 0, I can rewrite this as something of, or rewrite this entire condition based on f of x bar as something like this. Now I have an x bar wherein the momentum is 0 and f of x bar is known to me. So what consequently I can do is, I can expand my f of x, the function that tells me how my momentum is going to vary with position. I can expand it based on my x bar and write something like this. I have x bar, and at the x bar, the position or the momentum of my atom is 0. Maybe this position could be a stagnant or a flat surface in my cast. Supposing I am casting a specific shape, and in that shape there is some surfaces which ensures that the momentum of my atom is 0. So when I have such surfaces, the position, such atomic positions wherein the momentum is 0, it gives me an expression like this. And that position I assume it to be x bar, and it gives me an expression like this. Now with respect to my position, the x bar position wherein my momentum is 0, I'm expanding my f of x that dictates how my momentum is going to change with respect to my position. So with respect to my x bar, I'm expanding my f of x, which dictates how my momentum is going to change with respect to my position. So this is just a Taylor series expansion of my x of x that introduces my non-linearity with respect to my x bar, wherein the momentum is 0. So guys, I'm repeating it too many times. I understand that. The reason I'm repeating it is because every step has a physical significance to it. These are just not random variables that we have thrown in. They have significance, and that's the reason I'm just repeating it. I hope it's not too much. Now, if you consider this expression here, we already know that this term turns to 0 because this is how we introduced our x bar. This is by definition, this will turn to 0 because by nature, our x bar means at x bar, momentum is 0. So momentum is equal to f of x, and f of x bar is going to be 0. This is something that we have considered. Now, if you consider the other terms, so these terms here, what we are essentially considering is, we are considering the positions that are close to my x bars. So in x minus x bar, in all the cases of x minus x bar, this x indicates the position that are close to my x bar. So I have an x bar, and in this x bar, my f of x bar is 0, my momentum is 0. I'm considering all the position that is close to my x bar. So this means the x minus x bar, it tends to 0. It is close to my position. My position is close to my x bar, so x minus x bar tends to 0. So when I take the square of it and cube root of it and raise it to the power of 4, this becomes, or this tends more and more close to 0. So I can together ignore all the higher order terms. I can ignore my f of x bar because it is equal to 0. I can ignore my higher order terms because x minus x bar is close to 0. I am considering my x, which is the position of my atoms, that is close to my x bar, wherein the momentum is 0. When I do that, I end up having an expression something like this, wherein my f of x is equal to the derivative of x of x at x bar minus x minus x bar. My f of x is equal to the derivative of f of x at x bar, wherein the momentum is 0, and at the points, and we have x minus x bar, wherein x is the point close to my x bar. Now this f of x is equal to the momentum x of t, which we get from this expression here. When I substitute my f of x, the expanded version of it, and the, let's say, the curtailed expanded version, I know it's kind of a misnomer or oxymoron. When I curtail this expanded version or this Taylor series expansion and relate it to the f of x, I can further take this f of x, substitute it here, and I can bring in my momentum expression, and the momentum is nothing but change in position with respect to time. Now this expression, I can rewrite it as something like this. What I've essentially done is, instead of taking the derivative of my position with respect to time, I also introduce minus of x bar here. Of course, my x bar is a specific position, it's a constant. So it means my d or my dx bar by dt is going to be 0. It's just a trivial part, but still I'm introducing it here. So essentially what I end up having is, I end up having my momentum expressed in this way, and my function based on that dictates how much momentum my atoms experience expressed in this manner here. So basically both the sides of this expression have x minus x bar and x minus x bar. So this x minus x bar, I can write it as delta x and rewrite this expression as something like this. So x minus x bar, I can replace it with delta x, and this delta x can be substituted here, and the entire nonlinear expression can be rewritten in this way. Now, of course, we can rearrange this delta x and it adopts a form like this. Now, it appears to be a linear ODE which we can conveniently solve. And when you solve this, rather, you end up having an expression like this. When you solve this linear ODE, you end up having an expression of this form here. Now, this delta x is rather x minus lambda or x bar. So when you substitute it, you end up having x minus x bar and the solution here. So you have x minus x bar and the solution here, and ultimately you can express the position of the atom as the position wherein the momentum is 0 plus a term that includes the effect of the momentum on the function of the position. So basically what we have done is, we have considered an example wherein the momentum experienced by the atoms depends on in a specific way on the position of the atom, but we return it as f of x. And this f of x now tells us what momentum, how much momentum my atom is going to experience depending on its position. Now, in order to solve this expression, and assuming an x bar wherein my momentum is 0, that means my f of x bar is 0. I'm considering specific positions wherein my momentum is 0, that means my f of x bar is 0. So based on this f of x bar, I'm expanding my original function that brings in the nonlinearity. My original forcing term that brings in the nonlinearity, I expanded based on my x bar, which is the position wherein my momentum is 0. When I expand it, I end up introducing the first derivative of my function at x bar. When I expand it, all the other terms vanish away. All that is left with is the first derivative of my original function at x bar and an additional term x minus x bar, which we can replace it with delta x. Now, it is possible for me in this expression to solve for my delta x, because I have delta x here, I have x minus delta x bar here, x minus x bar here, meaning I have delta x in both sides of the expression, and this first derivative is with respect to a specific position. So I'm able to, this assumes a linear form, so I'm able to solve this. Again, this is a first derivative with respect to a specific position, so I'm able to solve this, treat this as a linear ODE, and I'm able to solve this. And when I solve this, I end up having an expression for my delta x, and my delta x is nothing but x minus x bar, so therefore I ultimately have an expression for my x bar. So x of t is nothing but my position of the atom. So what I'm doing is I'm describing my position of the atom when it is experiencing a momentum with respect to a position wherein my momentum is 0. So what essentially we are doing is, my molten metal experiences a momentum, and this momentum is a function, depends on, it is governed by the function of the position. So ultimately what we end up having is the ultimate position of the atoms under this condition when it is experiencing a momentum. That position of the atom, we express it based on the position wherein the momentum is 0. When I'm saying my atom experiences a momentum, and this momentum depends on a specific way on the position of the atom, that is f of x. Now ultimately I want to understand the position of the atom. Ultimately I want to know what is the position of the atom when it is experiencing a momentum of this kind. This position is now described with respect to another position wherein the momentum is 0. So that is how we have solved our non-linear ODE, and that is how we have correspondingly we have expressed the position of the atoms. Now what we are essentially saying is, when your atom is experiencing a momentum which is described as a function of its position, at the end of the day, when you want to understand the position of the atom, when you solve this expression and when you want to understand the position of the atom, you understand it with respect to another position wherein the momentum experienced by the atom is 0. So this is the way we can approach the non-linear ODE. Now, before we wind up or conclude this session, the non-linear ODEs, beside this example of casting, play a significant role when we are considering the position of the atom in a given potential field. A potential field, what we mean by that is a potential field. We mean that the potential energy experienced by the atoms depends on the position. And as the definition of potential energy goes. So when we say that the atom is present in a potential field, depending on the position, the energy experienced by the atom would vary in a specific way. Now, the force experienced by the atom in such a potential field, we refer to it in this manner. We have an atom in a potential field. The force experienced by the atom in the potential field is experienced by this expression here, or rather is expressed by this expression here. Again, when we say potential field, it means a potential energy field. Potential energy by definition depends on the position of the atoms. So when you have an atom that is present in a potential field, the energy of the atom varies with the position. The force experienced by the atoms is given by this expression here. When you rewrite this expression, you end up with a form like this. You end up with an ODE like this. So basically, when we are able to understand how to approach a non-linear ODE, even for the simplistic cases like this, we will be able to rather ascertain where my atom is going to be when it is placed in a potential field or when it is in the form of a molten metal and being poured into a cast. Again, the solution that we get when we take this approach is that the position of my atom as it experiences a momentum or as it experiences a force in a potential field, the position or the resulting position of my atom is expressed with respect to a position wherein the momentum is 0, a position wherein there is a linearity. So when I say the momentum is 0, this will turn to 0. So I have established a linearity because this non-linear term goes away. So when I am describing the position of the atoms in such a non-linear situations, what I'm essentially doing is I'm describing my position of the atom with respect to a position that introduces a linearity into my system. In this case, it was a position wherein the momentum was 0. In this case, it will be a position wherein my force will be 0. So, in this approach, when we describe the final position of the atoms, we are describing it with respect to a position wherein a linearity is introduced into the system. So, with this, we are essentially done with our discussion on ODEs, because we have considered linear homogeneous ODE. We have considered several techniques on how to approach linear homogeneous ODE. We have seen a couple of techniques on how to approach linear non-homogeneous ODE, and we have seen one approach on how to handle a non-linear ODE. So as the difficulty level increased, we have increased the number of approaches that we have taken, but still, at least if someone has, will you be able to solve a given ODE? At least by now, you should say, or at least you should know where to look for or what to look for when you attempt to solve such an ODE. If you are able to do that, if you are able to look at a ODE and then say, yeah, this could be solved, or I know where to look in order to solve for this ODE, then significant portion of this module or the significant portion of the objective that pertains to the module is achieved. So with that, we will wind up our discussion on ODE, and particularly on ways to solving the ODE. We will take up a new topic in the subsequent discussion. Goodbye.